Hi, everybody. I'm Stephen Heminger. I work for Microsoft, but I'm also very much involved with the DPDK and the Linux kernel. I am not one of the eBPF developers, even though there's some eBPF in this talk. It's not the main focus. I just don't want to see the button. There we go. I'll skip the table of contents to save time. So when I started this out, I was looking around. I said, in America there's a proverb that says, only a bad workman complains about his tools. And since I was coming to Belgium, I looked up. It turns out it's an old French proverb. Bad workers never finds a good tool. But then I started looking around. There's actually a Chinese proverb. So it says, to do a good job, a craftsman must sharpen his tools. And I do woodworking, and I've learned the hard way that unless you sharpen your chisel, you destroy things. And I think this is the same thing is true with the tool sets we work with. But before I go too deep into tool sets, I kind of want to throw up a big red flag to tell people, don't get too enamored with the tools. That's not what the most important thing is. The most important thing is figuring out how you're going to do it with a good methodology. So start out with a problem statement of what are you trying to solve? What's your workload look like? And what are your targets? And use a good methodology to actually do this in a structured, scientific process manner, not just throw it at the wall and see what sticks. And I'm not the person to go into detail about that, but you should really look up any of Brendan and Greg's talks on Linux performance analysis and the eBPF textbook that's now out from O'Reilly. Do some research, learn how to do it before you get too deep into playing with tools. But after I've thrown that out, now I'll go talking about tools. So in my life, we spend a lot of time working with DPDK applications. And a DPDK application, there's really two ways to look at it. One way to look at it doing analysis is to analyze the data, as in what's coming in and what's going out. This is traditional TCP dump packet filtering. So you basically have a mechanism to get the data to see what the application, why you're dropping packets, what's not going in. The other way to look at it is programmatically. And that's what tracing is. Tracing is all about, let's insert something into the program and see what we got. The poor man's way of that is print K. This is doing something smarter than print K. Figure out what's going on. Both of these are useful, and both of them are part of the solution. And on the packet capture side, traditionally, early days of DPDK, there was nothing. Like the first user survey feedback we got was, I need TCP dump. So Intel and a few others developed a packet dump for DPDK called pdump. And the way it works is your application is running as your primary application, and you have a secondary application that shares a ring with the primary application and captures packets. And the packets are outputted in PCAP format, and you put them somewhere. The problem with this is the implementation of this is very limited. You have no metadata, so you don't even know VLAN tags are gone. You have nothing about offload flags. What flow rule matched? So you have very little state in this packet capture. The implementation of this is not very robust, and the timestamp happens at the far end of the thing, kind of like you saw earlier when they talked about with collectee. It's the same thing, only at the DPDK level. The packet isn't being stamped when it's arrived, it's being stamped when you finally pull it off, which is pretty much useless. You have no direction information, so if you're capturing receive and transmit, you don't know which way this packet came from. And the current implementation only really handles a single port. So if I've got a router, I want to have both ends captured at once, put in one file, or you have to do something where you've got multiple files and try to correlate by timestamps. It's pretty hard. And lastly, there's no filtering. So there's nothing you just basically, you get the fire hose. And because of all this, the performance is pretty poor. So for what I've done working, it's not actually upstream. I did probe patches, they're still in progress, is to support PCAP and G in the DPDK. With that, you get 9 nanosecond time resolution. We can put system and interface data. If you're in the cloud, it's really important to be able to know, I got this data file I captured on a some node. What was the hardware on that node? What was the version of the firmware? All that can be put in the file that you got captured. It supports multiple interfaces, so you can have some 16-bit number of interfaces and put them all in one file and put them together. PCAP-NG supports flags for direction, and you can put the hash value of the packet and even comment strings of any other data you want. So really, it provides all that. So we're working out the details and all the API and ABI, but it'll definitely roll through. The next thing I've been working on relating to this is putting packet filtering into the packet capture. So the traditional way of doing that is with TCP dump is you start out with some nice text string like, show me all packets with the IP destination of FOSDEM.org, and libpcap does all the magic and produces a eBPF program. So the problem is we don't have a classic BPF interpreter in DPDK, and we really don't want to put one in. So we'll do the same thing the kernel does, which is translate that into an eBPF program. I've just worked with several people to get permission to take the same basic code loop that does that in the socket filter in the kernel, make it BSD licensed so that we can put that in the DPDK. So you just type, at the outer level, you put in the filter string, you get, and the lower level, you get the eBPF program, and then we can execute that in the DPDK with the JIT and everything else that's there. How am I doing it? On the tracing side, there's several options on Linux. I will have to admit, doing them in user space, none of them is ideal. But I'm going to describe 2 or 3 of them that I tried and how they work together and what it would look like. So first one was the Linux Trace Toolkit. It's been around a while. It's very easy to use and very well documented. Using it in user space, a typical way to use it is user-defined trace points, where you put trace points in your code, and then you can run filters at those trace points, and it produces common trace format data, which can then be digested. And it's from a user space tracing point of view, it's very high performance. It uses RCU and ring buffers, all those kind of performance tricks that DPDK does to basically get a fire hose of trace points and into user space. So my example with DPDK, implementing the test BMD application, DPDK, the one most commonly everybody seems to use. Oh, great. Well, I got messed up by some, never use tabs in slides. But if you look, the core loop of sending a burst of packets in the L3 forward application has a there, and you put a trace point in that says, hey, I got some packets. So you want to do the same thing with eBPF, kept from dtrace. They now have the ability to do this in user space. I'm kind of going fast. So the same thing in user space. This is with test PMD receive. You put a dtrace probe point in, and you get the same kind of thing. You want to use it. You end up using BPF trace, and you say, I'd like to pick up the user-defined trace point in test PMD, and I'd like this trace point, and you give it an expression of what you want. So I did an example doing BPF trace with test PMD and RX burst, and tell me the hash of how many packets do I get each time through the loop. Do I get a little or a lot? And this lets me decide if I should use bigger burst size, how much memory I should use, a whole lot of things. Well, the downside of this is you run some performance tests, and these are not real performance tests. That's what these slides are trying to say. This is not analytical, statistical, write a paper test. This is do a hack, do an unboxing. What am I getting? So I got two systems, one sending to the other one at full speed, 25 gig NIC. What does it cost me? Well, if I'm doing packet dump, so with packet dump turned off, having the infrastructure in place costs me nothing. But as soon as I start capturing, I get a 36% performance loss. Now, I did a hack, say, what if I had eBPF in there, and I said, in my capture filter, I evaluated, so don't capture this packet. So everything, it was just a null program that says no. That went from 36% to 0. So that says capturing with eBPF is going to work for what you want. You still have the problem of why is it taking so long in packet capture, but that's a different problem. As far as tracing with LTTNG, putting the trace point in costs you an insignificantly small amount of time, less than 1%. And when it's enabled, it was down to in the noise. So basically, at 25 gig, that trace point was costing me nothing. Now, that data may cost me something. BPF trace, putting the trace point in costs me even less because it's just a bunch of no-op instructions. But turning it on and to do that hash program would cost a 56% drop in throughput. So, kind of rushing here, but so we've got a bunch of ongoing work in the DPDK packet capture to try to give it full filtering. I've got a new version of the program because I want a user interface that looks more like T-Shark and less like a DPDK application because users don't care about all the wild and wonderful hardware flags that we love in DPDK. And there's ongoing discussion on the mailing list of how in DPDK we can have a standardized set of trace points so that other tools can get in and use them. And I wanted to leave some time for questions, so I sped up as soon as the flag went up. What? Oh. So I will now open the floor for some questions for a minute or two. Yes?
You mentioned that you are using eBPF filters to filter packets for capturing in DPDK. Does it mean that you re-implement the BPF virtual machine?
We have a eBPF virtual machine in DPDK. It's fairly limited right now in terms of there isn't a lot of hooks that use it, and it doesn't support maps and all the neat tricks you can do with eBPF. So it needs a lot more work, but it's there already.
But it's a complete separate code base from the...
It started out from a common code base, but it's maintained separately. And it was agreed, a lot of this is shared work with the developers of eBPF on Linux, so it's like, well, are we willing to BSD license this? And that's the biggest hurdle often. Other questions? Back there, Ray.
So, I was just looking at performance analysis. Is there a conclusion from your performance analysis in terms of, like, if you can realize the same function between using LTT compared to using eBPF, is that a recommendation to use the Linux tracing toolkit?
I think you need two things. One, with LTTNG, you can't do the at scale, run a program on the node to give me the results, and that's where BPF shines. So where BPF shines is if you're trying to scale out by using the compute resources at the trace point. Where LTTNG works really well is if you're saying, for security or other reasons, I can't run things in that environment, or it's an embedded system or something, get me the data and I'll process the data later. So my recommendation is abstract, like the classic Debian thing. If you can't make a decision, make both decisions. So have an abstraction that says, here's the trace points, and document that and let people choose for their environment which tool they'll use to put the trace point in. I got the time's up. Yes, Thomas?
How can we progress share the same source code for kernel BPF and DPDK DPF?
That's a good question. I really wish we could.
Are you volunteer?
I'm volunteer for too many things right now. I volunteer to help. That's about all I can do.
Thank you.
There you go.